November 7, 1940. Tacoma Narrows, Washington. The engineering calculations said the bridge was safe. European deflection theory promised that mathematical precision could build suspension bridges 60% lighter than American methods. 40-mile-per-hour winds should have been nothing for a structure designed by the most brilliant theoretical minds of the age. But that morning, something the computers couldn't predict began to happen. The 8-foot steel girders that mathematics said were perfectly adequate started moving like wings, twisting, oscillating, creating forces that existed nowhere in the theoretical equations. European precision engineering was about to learn what American hands-on builders had known for 70 years. Across the country, the Brooklyn Bridge stood motionless in similar winds, its massive open trusses splitting the air exactly as designed, not because of superior mathematics, not because of computer models, but because John Roebling had tested every piece of steel until it broke. At 11:07 that morning, the most expensive engineering lesson in American history was about to prove that some knowledge can only be learned by building, testing, and watching bridges move in the wind. The collapse taught engineers what modern computer models still miss. Spring 1869 marked the beginning of what European engineers called an impossible undertaking. The East River stretched 1,600 feet between Manhattan and Brooklyn, a churning expanse of water that had defeated every attempt at permanent connection. Ferryboats struggled against ice floes that could trap them for days, leaving two growing cities isolated from each other when winter storms descended on New York Harbor. The established wisdom from across the Atlantic was unambiguous. British suspension bridges had been collapsing in wind for decades, their failures becoming cautionary tales that crossed every engineering textbook. The Angers Bridge in France had killed 200 soldiers in 1850 when wind oscillations tore the structure apart in minutes. Between 1818 and 1889, 10 major suspension bridges had collapsed, creating a pattern of failure that European experts attributed to fundamental design flaws in the suspension principle itself. American engineers largely agreed with their European counterparts. Suspension bridges were beautiful but unreliable, suitable for light traffic across narrow spans but deadly when subjected to heavy loads or strong winds. The prevailing opinion held that any attempt to span the East River with cables and towers was engineering hubris that would end in catastrophe. John Augustus Roebling had spent 30 years building a reputation that challenged this conventional wisdom. The German immigrant had arrived in America with advanced degrees in engineering and philosophy, but his real education came from the wire rope factory he established in Trenton, New Jersey. While European engineers relied on mathematical theories developed in universities, Roebling tested every material until it broke, developing an empirical understanding of how steel behaved under stress that no classroom could provide. His early bridges at Niagara Falls and Cincinnati had proven that suspension spans could carry railroad locomotives and heavy traffic, but the East River presented challenges that dwarfed his previous work. The crossing required a span longer than any existing suspension bridge, with clearance high enough for the tallest ships entering New York Harbor. Wind pressure calculations showed forces of 30 pounds per square foot during storms, while the dead load of the structure itself would exceed 4,400 tons. Roebling's preliminary calculations filled dozens of notebooks with figures that seemed to defy engineering logic. The main cables alone would weigh 1,520 tons each, requiring anchorages that could resist pulling forces equivalent to the weight of entire city blocks. Live load capacity had to accommodate 144,000 people simultaneously. The entire population of Brooklyn could theoretically walk across the bridge at once without structural failure. European engineering textbooks offered no guidance for such massive loads across such distances. The longest successful suspension bridge in the world measured barely 800 feet between towers, half the distance Roebling proposed to span. Wind tunnel testing did not exist, leaving engineers to rely on mathematical models that had already proven inadequate for predicting bridge behavior in natural conditions. The wire rope manufacturer approached the problem with characteristically methodical precision. His factory workers subjected cable samples to loads far exceeding theoretical requirements, documenting exactly how much weight each wire configuration could carry before failure. This empirical approach revealed that American steel wire performed 33% better than European calculations predicted, providing safety margins that mathematics alone could not quantify. Roebling's design philosophy rejected the European preference for minimal structures that achieved elegance through theoretical optimization. Instead, he planned to build the Brooklyn Bridge 6 times stronger than calculations suggested it needed to be, reasoning that unknown forces and unforeseen conditions required engineering margins that no formula could predict. This approach had proven successful at Niagara and Cincinnati, where his over-engineered bridges continued carrying loads that would have destroyed more mathematically precise structures. The breakthrough insight that separated Roebling's approach from European methods concerned wind resistance design. Previous bridge failures showed a consistent pattern. Solid deck construction created wind pressure that caused dangerous oscillations. European engineers responded by making bridges lighter and more flexible, hoping to reduce wind forces through deflection theory. Roebling proposed the opposite solution: massive stone towers supporting an open steel truss system that would split wind flow rather than resist it. June 28, 1869, brought the project to an abrupt halt. While surveying the Brooklyn waterfront for tower construction, Roebling was positioning himself to take measurements when a ferry crushed his foot against the dock pilings. The injury seemed minor initially, but tetanus infection set in within days. 24 days after the accident, the master bridge builder died, leaving behind preliminary sketches and calculation notebooks that represented decades of empirical engineering knowledge. Washington Roebling inherited more than his father's project. He inherited the burden of proving that American hands-on engineering could achieve what European theory declared impossible. At 32, the Civil War veteran faced immediate pressure from politicians and investors who questioned whether any engineer could complete such an ambitious undertaking. The engineering establishment gave the project 6 months before collapsing under financial reality and technical impossibility. The young Roebling studied his father's notebooks and recognized the fundamental challenge that had killed previous suspension bridges. Wind forces remained unpredictable because no one had systematically tested how different structural shapes responded to varying wind conditions. European mathematical models assumed static loads and steady wind pressure, but real bridges faced dynamic forces that changed direction and intensity without warning. Standing on the Brooklyn waterfront where his father had died, Washington Roebling made the decision that would define both his career and the future of American bridge engineering. He would complete the East River crossing using empirical methods that prioritize physical testing over mathematical theory, building a structure so massively over-engineered that it could survive forces no equation had yet imagined. Washington Roebling rejected every piece of European bridge theory that had guided engineering practice for 50 years. Where continental experts relied on mathematical models developed in university laboratories, the young American engineer trusted only what his workers could test with their hands. His factory in Trenton became a proving ground where cables were stretched until they snapped, revealing the actual breaking points that European calculations consistently underestimated. The first breakthrough came from systematic wire testing that no European bridge builder had attempted. Roebling's workers subjected sample cables to loads increasing in precise increments, documenting exactly when each configuration failed. The results contradicted decades of engineering assumptions. American steel wire. Manufactured in Pennsylvania, foundries consistently performed 33% stronger than the best European specifications predicted. The superior performance came not from better raw materials, but from manufacturing processes that American industry had perfected through relentless experimentation. These empirical discoveries allowed Roebling to specify cable dimensions that seemed impossible to European observers. Each main cable would measure 15 3/4 inches in diameter, containing 5,434 parallel wires arranged in a pattern that distributed stress more evenly than any previous design. The cables alone would weigh 1,520 tons each, requiring anchorages carved from solid bedrock to resist pulling forces that could lift entire city blocks. Roebling's revolutionary approach extended beyond cable strength to the fundamental question of wind resistance. European deflection theory recommended lighter, more flexible bridges that would bend rather than break under wind pressure. This philosophy had guided recent constructions across the English Channel and German rivers, producing elegant spans that performed adequately in moderate conditions. But Roebling had studied every major bridge collapse of the previous 50 years, identifying a pattern that European engineers had failed to recognize. The destructive oscillations that killed bridges invariably began when solid deck construction created uniform wind pressure across the entire span. European bridges used continuous plate girders or solid roadway surfaces that acted like massive sails, catching wind and converting steady airflow into dangerous structural vibrations. Roebling proposed the opposite approach, an open steel truss system that would split wind flow into multiple streams, preventing the uniform pressure that caused catastrophic resonance. His truss design specifications defied conventional engineering wisdom about material efficiency. The supporting framework would extend 33 feet deep, creating a lattice structure that used 6 times more steel than European calculations deemed necessary. Each section would be fabricated from individual pieces small enough for workers to handle manually, then assembled on site using connections that could be tested and verified before installation. This modular approach allowed quality control impossible with the massive prefabricated sections favored by European contractors. The decision to use steel instead of iron represented another departure from established practice. Iron had dominated bridge construction for decades because of its predictable behavior and lower cost, but Roebling's testing revealed that steel offered superior strength-to-weight ratios when properly manufactured. The Brooklyn Bridge would require 160,000 tons of steel, more than any previous construction project in American history. Pennsylvania mills would need to develop new production techniques to meet specifications that exceeded anything previously attempted. Roebling's wire rope manufacturing experience proved crucial for solving the complex problem of cable fabrication. European bridges used cables twisted from smaller strands, a technique that created internal friction and stress concentration points where failures typically began. The American approach involved spinning cables from individual parallel wires, each carrying its precise share of the total load without the internal friction that weakened twisted designs. This parallel wire system had proven successful at Niagara Falls and Cincinnati, but the Brooklyn Bridge would require precision assembly on a scale never before attempted. The engineering specifications that emerged from 2 years of testing and calculation represented a systematic rejection of European minimalism in favor of American over-engineering. Suspender cables would number 2,100 individual wire ropes, each connection protected by zinc-lined fixtures, that Roebling called jewels because of their precision manufacturing requirements. The roadway would accommodate 6 lanes of traffic plus elevated railroad tracks, designed to carry loads that European engineers insisted would destroy any suspension structure. Wind tunnel testing did not exist in 1871, forcing Roebling to rely on observation and logical deduction to predict how his open truss design would perform in actual storm conditions. He studied the behavior of ships' rigging during Atlantic crossings, noting how rope and canvas combinations either caught wind destructively or split airflow harmlessly, depending on their configuration. The same principles applied to bridge construction, but on a scale that required unprecedented precision in calculating stress distribution across thousands of individual structural members. The breakthrough insight that would save the Brooklyn Bridge from the fate of its European predecessors came from Roebling's understanding that wind behavior changed dramatically with structural geometry. Solid surfaces created pressure that increased exponentially with wind speed, but open frameworks allowed air to pass through with minimal resistance. His calculations showed that a properly designed truss system would actually become more stable in strong winds, as increased airflow through the openings would create downward pressure that helped anchor the structure against uplift forces. Construction specifications reflected this empirical approach to engineering uncertainty. Every connection would be designed to carry 10 times the calculated maximum load. Stone towers would extend far below the high water mark, anchored in bedrock formations that geological surveys had mapped in unprecedented detail. The anchorages would be carved from solid granite, creating foundations that could resist cable tensions equivalent to the weight of several city blocks. By 1872, Roebling had transformed his father's preliminary sketches into detailed construction drawings that specified American manufacturing techniques for every component. European observers dismissed the design as wastefully over-engineered, pointing out that mathematical optimization could reduce costs by 40% while maintaining adequate safety margins. But Washington Roebling had learned from 30 years of his father's bridge-building experience that adequate safety margins existed only in theory. Real bridges faced forces that no equation could predict. Construction began with the most dangerous engineering challenge any American project had ever attempted. The Brooklyn caisson would descend 78 feet below high water mark, requiring workers to excavate bedrock while breathing compressed air that prevented the East River from flooding their underground chamber. No construction technique existed for such depths, forcing Roebling to adapt European pneumatic methods that had never been tested under American conditions. The caisson itself measured 170 feet long by 102 feet wide, essentially a massive wooden box with walls 7 feet thick at the cutting edge. Workers entered through airlocks that maintained pressure equivalent to diving 30 feet underwater, then spent 8-hour shifts digging granite with hand tools, while breathing air so compressed that flames burned differently and voices carried strange resonances. The Brooklyn caisson work began in March 1870, with teams of Irish and German immigrants earning premium wages for labor that everyone understood could kill them. Caisson disease began appearing within weeks, though no one understood what caused the mysterious symptoms. Workers emerged from their shifts doubled over with excruciating joint pain, some temporarily paralyzed, others suffering permanent brain damage from what physicians called compressed air illness. The bends, as workers named it, struck randomly. Experienced sandhogs who had worked compressed air projects in Europe collapsed alongside newcomers on their first day underground. Washington Roebling descended into the caisson regularly to supervise excavation, spending hours at pressure levels that European engineers observed only briefly during inspections. His hands-on management style, learned during Civil War engineering assignments, demanded personal verification of every construction technique. While European project directors relied on written reports from subordinates, the American engineer needed to see bedrock quality and foundation preparation with his own eyes. The Manhattan caisson presented even greater challenges. Initial surveys indicated bedrock lay 106 feet below high water, nearly 40 feet deeper than the Brooklyn Foundation. At such depths, compressed air pressure would approach the limits of human survival, requiring work schedules and safety procedures that no previous construction had attempted. European pneumatic engineering offered no guidance for excavations approaching 100 feet depth. By 1872, 20 men had died from caisson-related causes, their deaths attributed to various medical conditions that physicians could not properly diagnose. Compressed air illness remained a medical mystery, with symptoms ranging from temporary joint pain to permanent paralysis and death. Workers developed their own safety protocols based on observation, rising slowly from the caisson, avoiding alcohol before shifts, recognizing early warning signs that preceded serious attacks. Washington Roebling pushed himself harder than any worker under his command, spending entire days at maximum pressure to ensure foundation work met his father's exacting standards. The cumulative effects of repeated compression and decompression began affecting his nervous system by late 1872. Partial paralysis in his hands progressed to mobility problems that made supervising construction increasingly difficult. European medical experts consulted by telegraph offered no treatment for conditions they had never encountered. The crisis that would transform American engineering management struck in May 1873. Washington Roebling suffered a severe attack of caisson disease that left him bedridden and partially paralyzed, unable to leave his Brooklyn Heights home or personally oversee the massive construction project. Traditional 19th century engineering practice would have halted work until a new chief engineer could be appointed and brought up to speed on the complex technical specifications. Instead, Emily Warren Roebling made a decision that violated every professional convention of the era. The wife of the chief engineer began studying her husband's technical notebooks, teaching herself advanced mathematics and materials science through correspondence with university professors and consultation with the project's senior engineers. Within months, she understood cable theory, foundation engineering, and steel fabrication techniques well enough to make critical construction decisions. Emily's transformation from Civil War general's sister to practicing engineer occurred through systematic self-education that would have challenged university graduates. She mastered calculations for cable tensioning, learned to read architectural drawings that covered entire walls, and developed working relationships with contractors who initially dismissed her presence as an unfortunate domestic arrangement. Her ability to solve technical problems that stumped experienced construction supervisors gradually earned respect from workers who measured competence by results rather than credentials. The cable spinning operation began in May 1877, representing the most technically demanding phase of the entire project. Workers would walk across temporary catwalks suspended nearly 300 feet above the East River, guiding individual wires into position as massive cables took shape strand by strand. Each round trip across the span added just 19 wires to cables that would eventually contain 5,434 parallel strands. The work would require 14,060 miles of wire rope, more than the distance from New York to Hong Kong. Emily Roebling coordinated this dangerous operation from the construction site, making daily decisions about weather conditions, worker safety, and technical modifications that kept the cable spinning on schedule. Her presence challenged traditional gender roles while demonstrating that engineering competence could be learned through dedication and practical application rather than formal university training. Contractors and workers who initially questioned her authority learned to respect decisions that consistently solved problems and prevented accidents. The crisis that nearly destroyed the project struck in June 1878. A cable slipped during tensioning operations, killing 2 workers instantly and raising questions about the structural integrity of work completed to that point. Investigation revealed that contractor J. Lloyd Hay had substituted inferior wire for 80% of one main cable, delivering material that met visual specifications but lacked the strength properties Roebling's testing had verified. The cable fraud threatened to destroy not just the Brooklyn Bridge, but confidence in suspension bridge construction throughout America. European engineering experts pointed to the scandal as proof that American empirical methods lacked the systematic quality control that theoretical approaches provided. Insurance companies threatened to cancel coverage, and political pressure mounted to abandon the project before additional lives were lost. Emily Roebling faced the defining decision of her engineering career. The defective cable could be replaced at enormous cost and delay, or construction could proceed with reduced safety margins that still exceeded European bridge standards. Her husband's original over-engineering had designed the structure to be 6 times stronger than calculations indicated it needed to be. Even with inferior wire in one cable, the bridge would still be 4 times stronger than mathematical models required. She chose to continue construction, betting the project's success on her father-in-law's philosophy that empirical testing and massive over-engineering could compensate for problems that theoretical precision could not anticipate. The massive stone towers rose from their bedrock foundations like Gothic cathedrals dedicated to engineering precision. By 1881, each tower stood 276 feet above the high water mark, constructed from granite blocks quarried in Maine, and assembled with tolerances measured in fractions of inches. The towers alone contain 90,000 tons of masonry, more stone than most European cathedrals, anchored to foundations that extended deeper below water level than any previous American construction. Emily Roebling supervised the final phases of deck installation with the methodical attention to detail that had characterized every aspect of the project. The roadway system incorporated 6 lanes for carriages and pedestrians, plus an elevated promenade 15 feet above traffic level, creating multiple load paths that distributed weight across the entire suspension system. European observers noted that the deck structure alone used more steel than entire bridges they considered adequately engineered. The completed bridge represented total structural weight of 90,000 tons suspended from cables that had proven their strength through 15 years of systematic testing and empirical verification. Where European suspension bridges achieved elegance through mathematical optimization, the Brooklyn Bridge imposed its will on natural forces through overwhelming structural capacity that made failure virtually impossible under any conceivable loading conditions. Wind testing began during construction and continued through the final months of 1882. Workers reported that the bridge barely moved during 30-mile-per-hour gusts that would have set European suspension spans into dangerous oscillations. The open truss system performed exactly as John Roebling's empirical analysis had predicted, splitting wind flow into multiple streams that created downward pressure rather than the lateral forces that destroyed solid deck designs. The engineering triumph extended beyond structural stability to construction techniques that had revolutionized American bridge building. Every component had been manufactured to specifications that exceeded European standards, then assembled using connection methods that allowed individual inspection and verification before final installation. This modular approach ensured quality control impossible with the massive prefabricated sections that European contractors favored for economy and speed. Washington Roebling observed the final preparations from his Brooklyn Heights window, using a telescope to monitor details that his physical condition prevented him from inspecting personally. 14 years of construction had transformed him from a vigorous Civil War veteran into an invalid whose contributions to engineering history would be measured through the innovative management techniques his disability had forced him to develop. His empirical approach to bridge design had proven successful, but the human cost of pneumatic construction remained a cautionary lesson about the limits of 19th century industrial medicine. The moment that would vindicate 15 years of American engineering innovation arrived on May 24, 1883. Opening day ceremonies began with Emily Roebling driving the first carriage. Across the completed span, followed by President Chester Arthur and a procession of officials who represented both the political importance of the project and skepticism about suspension bridge safety that persisted despite successful construction. 150,000 people crossed the bridge during its first day of operation, creating live loads that European engineers had insisted would cause catastrophic failure. The structure carried this unprecedented human cargo without detectable deflection, proving that empirical over-engineering could achieve safety margins that theoretical calculations consistently underestimated. Pedestrians reported that the bridge felt as solid as walking on city streets, with none of the swaying motion that characterized European suspension spans. The engineering specifications that guided construction had created structural capacity far exceeding anything previously attempted. Main cables carried working loads of 11,000 tons each, while designed to support 65,000 tons before failure, providing safety factors of 6-to-1 that European practice considered wastefully excessive. The anchor systems could resist pulling forces equivalent to lifting entire city blocks, embedded in bedrock formations that geological surveys had mapped with unprecedented precision. Load testing continued throughout the summer of 1883, with elephant parades and military formations deliberately chosen to create maximum stress conditions. P.T. Barnum's circus elephants crossed the bridge in single file while military bands played, generating both live loads and dynamic forces from synchronized marching that European engineers predicted would trigger dangerous resonance oscillations. The bridge remained motionless during these demonstrations, its open truss design preventing the wind-induced vibrations that had destroyed suspension bridges across Europe. The triumph proved that American empirical engineering could achieve results that European theoretical methods had declared impossible. Physical testing of materials until they broke had revealed strength properties that mathematical models consistently underestimated. Systematic over-engineering provided safety margins that compensated for forces no equation could predict. Hands-on construction management had maintained quality control standards that theoretical specifications alone could not guarantee. European engineering publications grudgingly acknowledged that the Brooklyn Bridge represented a paradigm shift in suspension bridge design. The open truss configuration that American engineers had developed through empirical observation offered wind resistance properties that continental deflection theory had failed to achieve. More significantly, the construction techniques pioneered during the project had demonstrated manufacturing capabilities that European industry could not match. The bridge's performance during its first decade of operation confirmed every prediction that John Roebling's empirical analysis had made about suspension bridge behavior under real-world conditions. Windstorms that would have destroyed European spans created no detectable movement in the massive American structure. Traffic loads that exceeded the bridge's design specifications by substantial margins produced no signs of structural stress or fatigue. The combination of material over-engineering and aerodynamic design had created a suspension bridge that functioned more like a fixed span in terms of stability and load capacity. By 1893, the Brooklyn Bridge had carried millions of pedestrians and thousands of tons of cargo without a single structural failure or significant maintenance requirement. European engineers who had predicted catastrophic collapse were forced to acknowledge that American construction techniques had achieved suspension bridge performance that their theoretical model suggested was physically impossible. The empirical approach that emphasized physical testing and massive over-engineering had proven more reliable than mathematical optimization for predicting real-world structural behavior. The engineering lessons embedded in 14 years of construction would influence American bridge design for generations, establishing principles of empirical testing and conservative design that would save thousands of lives when future engineers face similar challenges with even more ambitious projects. The generation of engineers who emerged in the 1920s had been trained in universities that emphasized European theoretical methods over the empirical testing that had guided American bridge building for 50 years. Leon Solomon Moisseiff represented the pinnacle of this new mathematical approach, his brilliant mind capable of calculating structural loads and wind forces through elegant formulas that promised to revolutionize suspension, bridge design through scientific precision. Moisseiff's deflection theory offered seductive advantages that appealed to both engineers and politicians. Bridges could be built 60% lighter than the massive over-engineered structures that American empirical methods produced, reducing steel costs by millions of dollars while creating more graceful spans that matched European aesthetic preferences. The mathematical models seemed to prove that flexible structures could absorb wind forces through controlled deflection, eliminating the need for the expensive open truss systems that characterized older American designs. The Golden Gate Bridge, completed in 1937, became the showcase for deflection theory applied to American conditions. Moisseiff served as consulting engineer on a project that demonstrated how mathematical optimization could create suspension spans longer and more economical than anything John Roebling's empirical methods had achieved. The bridge's performance in San Francisco's challenging wind conditions seemed to validate theoretical approaches that European engineers had been advocating for decades. Washington State's need for a suspension bridge across Tacoma Narrows presented the perfect opportunity to prove that deflection theory could produce dramatic cost savings without compromising structural integrity. The original design by Clark Eldridge followed traditional American empirical principles, specifying 25-foot deep open trusses that would allow wind to pass through harmlessly. His conservative approach carried a total construction cost of $11 million, reflecting the massive over-engineering that characterized bridges built according to Roebling's testing philosophy. Moisseiff's counter-proposal revolutionized the project's economics through theoretical innovation that European mathematical models supported completely. Instead of expensive open trusses, deflection theory indicated that 8-foot deep solid plate girders would provide adequate structural strength while reducing construction costs to $6.4 million. The savings of $4.6 million represented the difference between European precision engineering and American wasteful overbuilding. The Washington State Toll Bridge Authority faced a decision that embodied the fundamental conflict between empirical and theoretical approaches to engineering. Eldridge's design followed proven American methods that had never produced a structural failure, but carried costs that seemed excessive when mathematical analysis suggested much lighter construction would perform adequately. Moisseiff's theoretical approach promised European elegance and economy, supported by calculations that appeared more scientifically rigorous than the rule-of-thumb methods that characterized older American practice. Economics prevailed over empirical caution. The authority awarded the contract to Moisseiff's design, trusting mathematical models that indicated 8-foot girders could handle all conceivable wind and traffic loads. Construction began in 1938, using European-influenced methods that emphasized efficiency and cost control over the redundant strength that American empirical engineers had traditionally specified. The completed Tacoma Narrows Bridge opened on July 1, 1940, immediately demonstrating behavior that Eldridge's empirical experience would have predicted but Moisseiff's mathematical models had failed to anticipate. The bridge moved noticeably in winds as light as 4 miles per hour, earning the nickname Galloping Gertie from workers and commuters who experienced its unexpected motion daily. Frederick Burt Farquharson, at the University of Washington, had been conducting wind tunnel experiments with scale models that revealed dangerous oscillation patterns in bridges with solid plate girder construction. His systematic testing showed that 8-foot girders acted like airplane wings, under certain wind conditions, generating lift forces that could twist bridge decks beyond their structural limits. The physical evidence from his laboratory models contradicted the mathematical predictions that supported deflection theory. Farquharson's warnings reached bridge officials through academic channels that carried less influence than the prestigious engineering consultants who had endorsed the theoretical design. His wind tunnel observations showed that solid girders created the same dangerous pressure patterns that had destroyed European suspension bridges throughout the 19th century. The empirical testing methods that John Roebling had pioneered 60 years earlier were revealing problems that mathematical analysis had overlooked. The morning of November 7, 1940, brought wind conditions that would test whether theoretical precision or empirical caution provided more reliable guidance for suspension bridge design. 40-mile-per-hour winds struck the bridge at 11 o'clock, creating forces that European deflection theory indicated should produce manageable structural response. Instead, the solid 8-foot girders began generating lift forces that mathematical models had never calculated. The oscillations that developed within minutes followed patterns that Farquharson's wind tunnel experiments had predicted with disturbing accuracy. The plate girders that deflection theory had optimized for economy were acting exactly like aircraft wings, converting horizontal wind flow into vertical lift forces that twisted the deck through angles no suspension cable system could accommodate. Torsional flutter began destroying the bridge using aerodynamic principles that bridge engineers had never considered relevant to their profession. At 11:07 that morning, the Tacoma Narrows Bridge collapsed in a spectacular demonstration of what happened when mathematical theory ignored empirical reality. The solid girders that European deflection theory had recommended as economical and adequate literally flew apart under wind conditions that would have caused no movement in Eldridge's open truss design. The disaster validated every warning that practical American engineers had offered about the dangers of abandoning empirical testing in favor of theoretical optimization. The catastrophic failure proved that John Roebling's empirical philosophy of physical testing and massive over-engineering provided more reliable guidance for real-world construction than the sophisticated mathematical models that had guided European engineering for decades. Wind tunnel testing, materials testing until failure, and conservative design margins had prevented exactly this type of disaster for 70 years of American bridge building. The collapse revealed that industrial-age methods of hands-on observation and systematic over-engineering could predict structural behavior more accurately than computer-age mathematical models and theoretical optimization. The most advanced calculations had failed to account for aerodynamic forces that any engineer who watched bridges move in the wind should have anticipated. Sometimes the most sophisticated technology could not replace an engineer's empirical understanding of how wind and steel interacted under real-world conditions. The lesson would need to be relearned repeatedly as each generation of engineers discovered that mathematical precision could not substitute for the hands-on testing that revealed how structures actually behaved when theory confronted reality.